Hello, my name is Udhiambo Nicholas Otieno, and I shall be taking you through algebra. And basically, we're going to begin from right from the beginning of what algebra is, define what algebra is, that is, what an algebraic term is, and see how we can form algebraic expressions, simplify them, and do all lot of operations around algebra. All right, so why don't we begin by defining algebra? All right, so we have the term algebra. Yep, so we have the term algebra. How do we define it? All right, so algebra basically is a branch of mathematics that uses letters. So the first thing it uses is letters, and numbers. It uses letters and numbers to form and solve mathematical problems. Okay, it is a branch of mathematics that uses letters and numbers to form and solve mathematical problems. So these letters that are usually formed out of these algebraic expressions are what we usually call variables. Okay, so they may include any letter, A to Z, or even lambda, Greek letters. Basically, they are unknown. And so usually in algebra, we try and find out what these unknown variables may be. Okay. And then the numbers that usually we have in these algebraic expression, we always call them coefficients. Okay, coefficients. All right, so these range from the numbers between basically negative integers, positive integers. They could be all numbers, they could be fractions. Anything that is numeric, they could be decimals. Anything that is numeric, we call it coefficient. Now, right now, let me give you an example of what I'm talking about here. So basically, for us to have a problem of algebra, or us to use algebra, we have to form what we call an algebraic term. Okay, so algebraic term usually is just a combination of variables and coefficients. All right, so we're looking at algebraic terms. Algebraic term. Very important that you know what an algebraic term is. So an algebraic term is basically a combination of variables and coefficients. For example, A is an algebraic term. Okay. All right. So this is an example of algebraic term. Another example that we can give of an algebraic term can be, let's say now we use a coefficient different from 1. Okay, so remember A is a variable and the coefficient there will be 1. So we can maybe, let's say, talk of 2b. So where 2 is the coefficient and b is the variable. So that is it. When we talk about what algebra really is, it's just a branch of mathematics that uses letters and numbers, or what we now know algebraic terms. All right, to solve, to represent and solve mathematical problems. Okay, so why don't we go ahead and do an example around this so that you understand exactly what algebra is. Awesome. So why don't we go ahead and solve this problem using algebraic symbolization. So basically the instruction in here is that we should use letters to represent the following statement. So this is exactly how algebra goes around, how algebra is used to solve problems in real life. So we're going to form an algebraic expression from the statement that you're seeing here. So we're supposed to write an algebraic expression for the sum of two consecutive integers. Of course, we know what integers are. They are negative and positive whole numbers. They are negative and positive whole numbers. So when we talk of 1 and it's -1, that would be an integer. Of course, 0 is also included there. 2, let's say -2, that would be an integer. So one thing I want you to note is that when we speak of integers that are consecutive, let's say 1 and 2, there is always a difference of 1 between them, because when you take, okay, when you move from 1 to 2, the difference between 2 and 1 is 1. So the sum of two consecutive integers, and this has to be an algebraic expression that represents any two consecutive integers across the board. So we're going to, let's say, we're going to let A, all right, let A be an integer. We're going to let A be an integer. It could be 1, it could be 2, it could be 3, whichever integer you want to call it. It could be 3. So A is basically a variable. It can be any integer, right? So we're going to let A be an integer. And so if we are to find the integer that comes after A, then note it will have a difference of 1. Okay, so whatever integer you take plus 1 should be the next integer after A. So in that case, the consecutive integer then will be, so consecutive integer to A will be A plus 1. All right, so therefore we'll have a situation where we have A followed by A plus 1. And so if we want to find the third integer, the third integer after A, then you notice we just have to add 1 to A plus 1. Okay, and that will be A plus 2. Okay, A plus 2. Yeah, so basically that goes on and on and on until whatever number of integer you want to represent from this particular problem. So that is an example of how we can use algebraic terms to form problems and maybe solve them. Thank you. Let us look at another. Let us then go on and solve and simplify algebraic expression, in the next class. Yes, so moving on to simplification of algebraic expression, I want to introduce a new term that is greatly going to help you with problems that involve simplifying algebraic expressions. And that is a term like and unlike terms, okay? Like and unlike terms. So at what point do we say that terms are like? And at what point do we say that terms are unlike? All right. So terms are only like if they are of the same letter. Okay. If they are of the same letter and they are raised to the same power. Okay. Raised to the same power. So it is only these two conditions that it is only these two conditions that qualify a term to either be like or unlike. So for like terms, they have to be of the same letter and they have to be of the same power. All right, so let us give an example of maybe a like term. That would be A and let's say 2A. A and 2A would say that these ones here are like terms. Why? Because both of them are of the same letter A. And of course, when you look at the A is raised to what? The power of 1. Now, this would be different from assume A and, of course, let me just use this, A squared. So A and A squared won't be like terms. A and A squared won't be like terms. Why? Because we have A raised to 1 and A raised to 2. Remember, for it to qualify to be like terms, then both of them, other than being of the same letter, must have equal or the same index. Okay? So that's it with like and unlike terms. Let's go ahead and handle an example from that so that you probably have a proper understanding of what we're talking about. Yes, example 1. So simplify 3x plus 4y minus x plus z plus 3y. So basically, for us to simplify this, what we are going to do first of all, and what we're looking to do, is basically bring like terms together, add them where terms need to be added, and subtract where terms need to be subtracted, and that will basically be it for this particular problem. So note 3x as a like term with negative x. All right, so we'll have 3x minus x, okay, plus 4y. Okay, so 4y as another like term with 3 is the same like term with 3y. So we'll pair them together, plus 3y plus z. All right, now that we have the like terms together, basically we are going to add and subtract where we have to do so. So 3x minus what? X will give us 2x, these two here, and 4y plus 3y will basically give us 7y plus z. And so that will be it for this particular problem. And let's see if you can handle even further complicated example in example 2. Awesome. For example 2, we have in half a minus a third b plus a quarter a. So the same thing, we bring the like terms together, add and subtract where we have to add and subtract. All right, so basically I have a as the same like term is of the same like term as a quarter a. So that will pair them together. All right, minus a third b. All right, so having grouped them together, for us to simplify it further, we're going to find the LCM of all our denominators, which in this case will be the LCM of 2, 4, and 3 will be 12. All right, so 12 divided by 2 will be 6. 6 times 1a will basically be 6a. All right, then we'll have 12 divided by 4, that will be give us 3. 3 times a basically will give us plus 3a. And on the other end, we'll have 12 divided by 3 giving us 4. 4 times b will give us 4b. Awesome. So to simplify this further, we're just going to add the like terms together, and that will be it for this. So that will be 6a plus 3a, and that will give us 9a minus 4b, all of that all over 12. And so that would be the solution to that particular problem. Yeah, awesome. So for our last example, we are going to handle this simple problem. So basically, we're supposed to simplify 5a plus 2a squared plus 10a. This should be easy. Probably, if you can recall the definition of like terms, you can pause and try solve it for yourself. So we say that like terms, other than having the same letter, must also have the same index, all right, in terms of its power. So that means that 5a and 2a squared are not like terms. However, 5a and 10a are like terms. Why? Because a is raised to the power of 1 here, and a is also raised to the power of 1 here. And why are these two not the same term as, why are they not like terms with 2a squared? That's because a squared here is raised to the power of 2, whereas the other ones have an index of 1, all right? So basically, we're going to group the like terms together and add where we need to add, and that basically will be the solution to this problem. So therefore, that's going to leave us with 5a plus 10a. Okay, those are like terms, plus 2a squared, because it's an unlike term compared to the others. So 5a plus 10a basically will give us 15a plus 2a squared, and we'll leave our answer at that in this particular problem. All right, I want to thank you for your time, and I'll see you in our next class in this algebra series that I am designing for you. Thank you. Have a good one.